to be talking about energy. We want to be able to use mathematical models to represent different types of energy by the end of this presentation. Now, we're not going to talk about every type of energy, but we are going to talk about a few different types. First, though, energy it comes in things like chemical, nuclear, internal energy. Internal energy, we deal with things like heat and friction and things like that. There's potential energy, there's kinetic energy, and Q is heat. It's any other form of diffuse energy like heat, sound, or light. So it's kind of that extra of, like, if you lose some of your energy, where did that go? You didn't actually lose it. It just went to heat or sound or light. So it transformed into a different type of energy. But we'll talk about energy transformations in a few more videos. Not yet. Anyway, so first let's talk about the unit for energy. We know that units are very important. For energy, we use the unit joule. And let me tell you a little bit about a joule. So 1 joule is equal to a kilogram times a meter squared divided by a second squared. You could also write it as a kilogram times a meter per second squared times a meter, or a newton times a meter, or a Pascal meter cubed, or work times second. A watt times a second.
When the sunlight strikes raindrops in the air, they act like a prism and form a rainbow. The rainbow is a division of white light into many beautiful colours. These take the shape of a long round arch with its path high above and its two ends apparently beyond the horizon. There is, according to legend, a boiling pot of gold at one end. People look, but no one ever finds it. When a man looks for something beyond his reach, his friends say he is looking for the pot of gold at the end of the rainbow. Throughout the centuries, men have explained the rainbow in various ways. Some have accepted it as a miracle without physical explanation. To the Hebrews, it was a token that there would be no more universal floods. The Greeks used to imagine that it was a sign from the gods to foretell war or heavy rain. The Norsemen considered the rainbow as a bridge over which the gods passed from Earth to their home in the sky. Other men have tried to explain the phenomenon physically. Aristotle thought that the rainbow was caused by reflections of the sun's rays by the rain. Since then, physicists have found that it is not reflection, but refraction by the raindrops which causes the rainbow. Many complicated ideas about the rainbow have been formed. The difference in the rainbow depends considerably upon the size of the water drops, as the width of the coloured band increases as the size of the drops increases. The actual primary rainbow observed is said to be the effect of superpositioning of a number of bows. If the red of the second bow falls upon the green of the first, the result is to give a bow with an abnormally wide yellow band, since red and green lights, when mixed, form yellow. This is a very common type of bow, one showing mainly red and yellow, with little or no green or blue.
So that was James Prescott Joule, and in fact, while he talked about rainbows, and we'll talk more about diffraction and refraction, which is something he mentioned in his little speech there, he is in fact the person that the Joule was named for, and he lived from December 24th, 1818 to October 11th, 1889. So he was a English physicist and a brewer.
Booyah!
And he was born in Salford, Lancashire. So first, so we're going to move on to different types of potential energy. And in this class, we talk about 2 different types. So first, we have gravitational potential energy. And in the reference table, this is missing. But this means that it is gravitational potential energy. And it's important that you know that this is gravitational. In the reference table, it just says it's PE. It doesn't have the little g. But this is gravitational. It's not all potential energy, just when it's from a height. And its equation is mass times the acceleration due to gravity times delta H. And this right here is, again, the change in. We've dealt with this many times already this year. But we will often make it so that it's from a height and it goes down to the ground, which is 0. But you can go from a height to somewhere else in there, and just that change is what we're looking for, and that would be the potential energy that it has at that time. Okay, the other type of potential energy is the potential energy of a spring, and its equation is 1/2 times K, which is the spring constant, times x squared. As I said, K is the spring constant, so it's how hard is it to stretch, and we'll talk more about K in a little while, in like in 2 more videos, I think. And then x is the distance that spring is stretched. So again, there will be more on springs later this week in another couple of videos. So here is an example. It says a 1 kilogram rock is at the top of a cliff 90 meters high. What is its gravitational potential energy? So we want to write our knowns. We have mass is 1 kilogram. The initial height is 90 meters. The final height is 0 meters because it lands at the ground. And then we are looking for the potential energy due to gravity. So the equation we use is mass times the acceleration due to gravity times delta H, and it is 1 times 9.81 times final minus initial, and we get minus 882.9 joules. But we're just going to deal with the positive right here. So it's 882.9 joules, and that's what we want right now. So it says, this is the second example. It says a spring has a spring constant of 50 newtons per meter, and it is stretched 0.2 meters from its rest position. What is the potential energy stored in the stretched spring? So we have K of 50 newtons per meter. The X is 0.20 meters. And the potential energy of the spring is what we're looking for. The equation is equal to 1/2 kx squared, and it's 1/2 times 50 times, okay, let's try this again. So it says a spring has a spring constant of 50 newtons per meter, and it is stretched 0.2 meters from its rest position. What is the potential energy stored in the stretched spring? So K is equal to 50 newtons per meter. X is equal to 0.2 meters, and we're looking for the potential energy of the spring. The equation of potential energy of the spring is going to be 1/2 kx squared, and it's times 50 times 0.2 squared, and you end up with 1 joule. So that's how you solve this. So these equations are pretty simple. Things will get a little more complicated as we go, but for right now, this is what we want to see. So then the next thing we're going to deal with is kinetic energy. The equation for kinetic energy is 1/2 mv squared, where the more velocity is more energy, more mass is more energy. So here we can see that it's going really fast, so it has more energy. So here we have a 45 kilogram boy is riding a 15 kilogram bicycle with a speed of 8 meters per second. What is the combined kinetic energy of the boy and the bicycle? So we can say that the first mass is 45 kilograms. The second mass is 15 kilograms. The total mass is 60 kilograms. That's just adding these two up. And then we have the velocity is equal to 8 meters per second. And then the kinetic energy is what we're looking for. the total kinetic energy. So that means that we want Ke equals 1/2 mv squared. And we're looking for 1/2 times 60 times 8 squared. And then we get 1920 joules. And that is our answer.